we can move on to our third slot. Our third slot will be continued with a title about Interzeolite transformation technique to understand the formation of unusual zeolites. And it will be presented by Dr. Rino Rakhmata Mukti. Some information regarding our presenter today. He is a lecturer at the Inorganic and Physical Chemistry Division, Bandung Institute of Technology Indonesia, ITB. Dr. Rino research interests are on the synthesis of zeolite-based catalysts by using sustainable natural precursors, catalytic upgrading of petro and biofuel, mitigation of hazardous waste or chemicals. He is also the fellow of Indonesian Academy of Young Scientists, ALMI. He received a lot of awards such as the 14th Ahmad Bakri Award and the AAD Fraunhofer Technopreneurship Award, bis Natalis, FMIPA ITB Award for Excellence in Research. He also received the Indonesian Young Material Scientist Award and Asian Rising Star Award at the 15th ACC from Nobel laureate Professor Negishi. So without further ado, I would like to welcome Dr. Rino Rakhmata Mukti to deliver his sharing. Please welcome, Doctor.
Thank you, Dr. Harris. Can you hear my voice?
Yeah, loud and clear, Doctor. Please
Okay.
continue.
So, well, it is very grateful today to be invited in this conference, and I meet again my good friend Engpo, and also regard to Prof. Osumanu. Thank you. I enjoy your presentation this morning. I would like to thank also to the organizer, Dr. Tengku. Thank you. Nice that you send me a text, and as well as the, I think it's leaking. Can you mute the participants?
Student, please mute your...
Okay, it's done. Okay, and I would like to thank to also to Dr. Nick Ahmad Nizam, and also happy to hear that the Persatuan Zeolit Malaysia finally established, and looking forward to collaborate with the MYZA, MyZA. Today, the presentation that I would like to bring actually what we have done recently, and we were interested to study the interzeolite transformations to understand the formation of the other zeolites. So, of course, many zeolite scientists are now interested with these topics in order to further understand the formation mechanisms. The interzeolite transformations actually has several benefit applications, and for example, that this interzeolite transformation may help to simplify the synthesis procedure to avoid the use of the organic compound, for instance, in order to synthesize zeolites. Well, this transformation of the interzeolite may also help to further rearrange the atomic structure. For instance, if we would like to locate the aluminum atom precisely in such environment in the framework of zeolite, then we can probably make some strategy with this technique. So it also helped to use these zeolite waste. If we have a zeolite waste, then we can further process, still use it and transform into the more useful zeolite. Well, the other application also, if used to find the most difficult zeolite that that can be synthesized. For example, in the support type LTL, yeah, perhaps it's quite difficult to synthesize using the bottom-up procedure. Then the interzeolite transformation from the support 37 can help to realize this LTL type support. And the other report also mentioned that the interzeolite transformation technique is also useful for metal encapsulation. That is very important in order to use the zeolite further as a catalyst in such industrial demanding reactions. Well, today the conference theme about agriculture. You can see my slide full, right? Because I'm seeing in my slide there is some a shortcut I cannot remove, but I hope it's not disturbing. Okay, I can remove now. Today the conference theme is to use the zeolite in agriculture. Of course, there are a lot of applications of zeolite in agriculture. Yeah, so we would like to, for example, we would like to retain the nutrients, yeah, and water in agricultural soils. Already explained by Prof. Prof. from Brunei this morning. So with relation with these themes, actually, we would like to present today's that we also have some topics of using natural zeolite, so-called natural zeolite from the Indonesian deposits. We have a lot of deposit throughout the Indonesian island. One of the deposit actually came from the Sulawesi. Like if you can see this map here, Sulawesi is somewhere near the Borneo island. And we actually received this sample from the students in the university in Sulawesi. So we collaborate with the Universitas Hasanuddin in Makassar, Sulawesi, and we received this so-called natural zeolite sample. And we examined the sample using the XRF at first, and we confirmed that the composition mostly are aluminosilicate materials. So that zeolite itself is defined as a microporous crystalline aluminosilicate materials. But if we characterize with the XRD, so when we look at the diffractogram, well, we hardly see any pure zeolite phase, any of the zeolite structure. So it's consists of the unknown crystal phases, unfortunately. But everybody call this natural zeolite that we also complain about that. That's why since it has still aluminosilicate content, we would like to further study, further process these materials, these natural aluminosilicate materials. So we use these materials at first as a seed. We dissolve this material in the basics conditions using sodium hydroxide, and we put it in autoclave. And we hope that we could somehow transform this material into zeolite, some zeolite. And we compare the synthesis using the other technique. For example, we also use this as a seed with additional precursors of silica and alumina. And we compare also the result with the procedure without using this as a seed. In addition of the silica precursor and alumina precursors. And we could, if we see the results, these natural aluminosilicate material from Sulawesi, well, finally it can transform into Ana zeolite ANA zeolite, after hydrothermal treatment at 170 degrees Celsius for some time. And then if we also use the additional precursors, silica and alumina, in such composition, and we use this aluminosilicate material as a seed, we also obtain ANA. So ANA most probably already in the sample of the natural aluminosilicate. Perhaps this natural aluminosilicate material has a fingerprint of ANA, we believe. So we further continue extend this study. Of course, we know that the synthesis parameters of zeolite, we can vary the temperatures, we can vary the time, as well as the pressure. And we are interested to see whether if we apply such a hydrothermal treatment with lower pressure, perhaps it may give such a difference in the zeolite result. Yes, indeed. When we apply the lower pressure of the hydrothermal treatment using the propellant bottle instead, then we obtain we didn't obtain ANA zeolite when we transform these aluminosilicate natural materials. So instead we obtain GIS zeolite, as shown in this picture. So we characterize the sample by looking at the, of course, the diffractogram and the SEM image. So we obtain GIS zeolite in addition to ANA when we apply the lower pressure of hydrothermal treatment. It's very interesting. So our question is why this GIS framework occur. So if we look at the structure of the zeolite framework showing ANA and GIS, they have some common structure, especially in the secondary building unit, not the composite building unit. So we hypothesize that this common secondary building unit may be the reason why the GIS can be present in addition to ANA. And we also understand that the ANA zeolite framework has very complicated structure. So we call it distorted framework. Yeah. And then this distorted framework requires normally higher synthesis energy. That's why the higher pressure is needed to transform into a more complicated structure such as ANA compared to GIS. And since we have this common secondary building unit, it could probably also that the probability of the interzeolite transformation may occur. For example, GIS to ANA. But still, of course, we need some proof. The other variation of the synthesis, we would like to apply the different precursor source, such as silica precursor. So we were using colloidal silica in the previous experiments, and we would like also to try the organic silicon precursor, such as TiOS, because TiOS dissolve faster. And when the dissolutions, when we have the faster dissolution, it in principle it will influence the formation of the nuclei before the crystal growth of zeolites. So we would like to see whether the TiOS precursor may give some impact. And if we look at the result here, indeed, these different silica precursors, in this case, TiOS was used, and in the end, we also we have the other framework of zeolite form, in which this is a sodalite form. So in addition to ANA, we also have we can have sodalite zeolite as a result from using the thios as precursor, alternative precursor. So we hypothesized that the faster thios dissolution lead to faster nucleation. So the larger the number of the nuclei produced during the synthesis, so it will give some maybe supersaturation condition, and the 2D growth, 2D framework growth is favorable compared to the 3D framework growth. Yeah. So when we compare Zeolite to ANA, for instance, and we look at the structure between the Zeolite, ANA, and GIS, of course, Zeolite and GIS has some common secondary building unit with the ANA. So perhaps this hypothesis may answer why the Zeolite can be present in addition to GIS along with the ANA. Yeah, so we confirm that the role of the seed, yeah, in this case, actually natural aluminum silicate materials from the Sulawesi Island, when we use as a seed, so it will influence also the yield, yeah, or yield percentage when we have seed, when we use this material as a seed. So of course we have more yield compared to the without seed zeolite. So, and the crystal size, when we hypothesize that the number of nuclei is larger compared to the when we use the other silica precursor, so then when we have a larger number of nuclei, of course it will somehow inhibit the crystal to growth. So the crystal size when we have a seeded synthesis is lower compared to the unseeded. So this is the first conclusions that the possibility of interzeolite transformation may occur when we use these natural aluminum silicate materials as a seed, and then several zeolite forms such as GIS and Zeolite. Of course, further investigations shall be further carried out to understand further. Dr. Haris, we have more time, or how much time I have left?
I think you're allocated for half an hour.
And still how many minutes?
Yeah, I think you can go to 10:30, I think.
10:30.
Yeah, I think about
Okay,
like 10 minutes
10
more.
minutes. Okay. So
Yeah.
in the next discussion, actually, I would like to discuss to present that we still, when we talk about interzeolite transformation, we still not sure. We are still not sure whether the mechanism will go through the recrystallization. That means the zeolite will be what do you call this, will be dissolved and then recrystallized back, or probably the mechanism will go through the diffusionless. That means the transformation from one zeolite to another may occur in such one click. Yeah.
Sorry, doctor.
Sorry.
You can have until 11 actually.
Oh, okay.
Yeah,
No, I think
still a lot of time.
I need
Sorry.
some 10 minutes. It's fine.
Yeah.
Yeah, so we are interested to somehow what do you call this, modify the to trick the synthesis procedure. So during the transformation of the interzeolite from one zeolite to another, so within the zeolite parent, actually we would like to introduce some organic compound into the micropore structure. So the idea is to constrain the micropore structure, and as well as to stabilize, to maintain the micropore structure against the interzeolite transformation. So we hope that if we introduce the organic compound into the micropore of zeolite parent, then it will not be destroyed when it transforms into the other zeolite. So we know that since of zeolite is normally using the organic compound as the structure directing agent. So we also interested that the structure directing agent may also play roles in forming the target zeolite. For instance, MFI zeolite actually is can be synthesized when using the structure directing agent from the organic compound such as tetrapropyl ammonium ions. So when we use this tetrapropyl ammonium constraint in the zeolite parents, for instance, if we want to convert beta zeolite to MFI, and we constrain the micropore of the beta zeolite with the tetrapropyl ammonium, then since the tetrapropyl ammonium is also the structure directing agent for the MFI, then the zeolite target should be MFI, and it shows in the previous reports recently. We also try to understand the other interzeolite transformation using the organic compound. For example, the fojasite to beta. We know that the beta synthesis of beta is using tetraethyl ammonium ions. So this organic compound, tetraethyl ammonium, we would like to constrain in the fojasite, and we would like to see whether the beta can be still formed as a target zeolite. Yeah, so first we constrain of course we synthesize fojasite zeolite by some procedure using the hydrothermal treatment in the absence of organic compounds, and then after that we like to constrain the organic compound, which is tetraethyl ammonium, into the fojasite framework. And by looking at the diffractograms after the confinement of the organics, we see that the crystallinity is quite stable. Then we can proceed into transforming into the other zeolite. And when we see the transformations when the tetraethyl ammonium organic constraint in the fojasite zeolite. So finally, we didn't obtain beta zeolite, but we obtained the other zeolite such as chabazite and merlionite zeolite. Yeah. There are two zeolite as a product when we transform the fojasite in the condition of the organic constraint in the micropores framework. And it is very interesting, especially when we try to increase the organic content in constraint in the micropores of fojasite from 0.25 molecule per unit cell of fojasite to 1 molecule per unit cell of fojasite. So we can see that there is an increased fraction of merlionite zeolite compared to the chabazite zeolite. So somehow the merlionite zeolite and chabazite zeolite is trading off as a product when we increase the organic compound constraint in the fojasite zeolite. So why these two products, chabazite, merlionite, can form? We understand actually if we convert fojasite to chabazite, because they have common composite building unit this time, CBU. Not only the secondary building unit, but the CBU composite building unit that is more complex. They have a similarity. Then we understand that this can be transformed into chabazite. But when the chabazite transformed to merlionite, this has a lot of questions, because there's no similar common composite building unit, CBU. So at the moment, we only understand that probably some similarity of 8-membered ring. Yeah. And the potassium ion used in the synthesis may maintain the 8-membered ring unit, That is why chabazite can be transformed into melanite, since they have similarity only in 8-membered ring. I think this is a very interesting subject to be further continued, especially by using computational tools. Yeah, we show that the chabazite can have a trade-off with the melanite product of zeolite. The fraction of melanite zeolite increase, and the fraction of the chabazite zeolite decrease when we increase the organic compound confined in the framework of the parent zeolite, which is fugicide. Then the question is whether this is going through the recrystallization mechanism or the diffusionless. Yeah, the diffusionless may also understand as reconstruction. So we probably at the moment conclude that since the organic is confined into the zeolite parent framework, and it has 1 molecule per unit cell of organic, then probably this may not go through the recrystallizations. So the parent zeolite may not be destroyed and then recrystallized back into the new zeolite, but instead perhaps the reconstruction may occur, so without destroying much of the zeolite parents. Yeah, so the debate is whether this is going through the recrystallization or reconstructions. From the fugicide to chabazite, of course, we understand because it has some common composite building unit. But from chabazite to melanite, we propose that the reconstructions also plays role as a formation mechanisms. But of course, we still want to investigate this further when we try to understand whether it is going through recrystallization, either recrystallization or the diffusionless or reconstruction mechanisms. Yeah, so for the second summary, we would like to conclude that the Interzeolite transformation may be studied using the organic confined technique. So we would like to confine the zeolite parent framework in order to understand further whether the mechanism is going through the recrystallization or the reconstruction. And we're surprised that we see some MYZA form in addition to chabazite zeolite, and the fraction of MYZA zeolite can be increased with increasing the organic content confined the zeolite parent. I think this is a new report so far. I haven't seen any similar report reporting the increased fraction of MYZA zeolite during the interzeolite transformation. So I would like to thank my students. This is us with the zeolite shirt. I think everybody's welcome to visit Indonesia, especially to visit our campus in Bandung, ITB, Institute Technology Bandung. And of course, we will reserve the shirt, the zeolite shirt, for anybody who will visit us. So this is actually in front of the iconic building of our campus. Our campus actually was built in 1920 by the Dutch. Actually, we were Delft University in the beginning, and then converted to ITB in 1959. Yeah. So everybody is welcome to visit ITB. And thank you very much for giving me some opportunity. Thank you.
Okay, thank you to Dr. Rino Rakhmata Mukti for your very interesting sharing. Yeah, I